All right, cool. It is, thank you for the introduction. It's a really great pleasure to be here. The Reaktor people have been awesome, so shout outs to them. Yeah, so I titled the talk, A Case for Oxidization. Clearly we're gonna be talking about rust here. And oxidization is the process by which we get rust, in case that wasn't clear. Yeah, so let's get started here. I want to start with a personal story, and then I'll actually tell you what I'm going to talk about. But I think it'll become clear you already know what I'm going to talk about, but it'll become clear why I'm going to talk about it through this personal story. So about 5 years ago, I was at MIT doing my master's, and I was interested in operating systems and all this kind of thing. And in particular, I was interested in using high-level languages to write operating systems. Like, could we write an operating system in Python? Probably a bad idea, but could we do it? Could we do it in Haskell? What would that mean? Would that be a good idea? So I did this thesis, and the title of the thesis was Exploring OS Development with High-Level Languages. That's sort of, that's what I just said. The subtitle of the thesis was, But Without a C Runtime. So it was really important that we're trying to use these high-level languages, presumably to get security and correctness out of our operating systems. And then if we toss C underneath all of it, if C is the thing that's really powering my Python or whatever it is, we're probably not really doing much better than the status quo. So the fact that we use C to run a high-level language, probably not a good idea. So the gist of the research was, can we find programming language primitives, programming languages, programming language properties that we can somehow convince ourselves lead us to writing better operating systems. So the way I did this was to basically write an operating system in all of these languages. So I wrote a tiny operating system in every single one of these languages. I'm not going to read them out. You probably know about most of them. You probably don't know all of them. Some of these are research languages. Some of these are esoteric languages, including Rust at the time. But I went ahead and just wrote an operating system in every single one of these languages just to see what it was like. Just to see if I could maybe convince myself that there was a point to doing this and that there were good language properties that somehow enabled us to write secure, correct operating systems. And this was really sort of a throw 100 darts at the wall and then see what sticks kind of thing. There wasn't like a really great research process to this. It was like, let's write a bunch of operating systems. So I did that. And sort of a few properties became clear that we would want to use for writing operating systems, and ideally we get correct secure software out of it. And sort of the implication of doing this was that if it kind of worked out for operating systems, if I could find these properties that worked for operating systems, then those properties would probably make themselves amenable to writing just general system software, file systems, databases, things of that nature. So I went ahead and did that, and I found a few properties that seemed like really important to this kind of work. In particular, we really wanted memory safety. The days in C and C++ are numbered. Like, we just don't want to segfault when our kernel is running, ideally because that means the entire machine crashes. We also wanted a very minimal runtime. Again, because if this runtime is written in C, then we're really not doing any better. And because we're lazy and porting a runtime into bare metal is just not fun. And we also wanted a nice, strong type system, ideally so we could encode properties as part of types in our software, and have the type system sort of protect us from ourselves. And finally, we are writing an operating system, we're writing a kernel, we're writing system software, so clearly this thing needs to be performant. Now, I have Haskell on the list here, but really it should be like half a Haskell, because I started writing this operating system, and then it got to the point where I was writing the thing, and I needed it to run. And that meant porting the runtime, which is about 50,000 lines of C code, and I gave up halfway through, and nothing ever ran. And I was like, okay, I love Haskell, but definitely not for writing operating systems. So this was the list. And then you kind of just biject the list with the properties of each of these languages, and you figure out sort of what's going to work. So we do this table here, and we put some check marks here and there, and then we see, hey, which languages have all the check marks? And for those of you that love a particular language on this list, and I'm misrepresenting that language, I hear you, I'm with you. It's sort of hard to just have check marks. So bear with me on the list here. So if we look at this, you can see that there's 2 languages that have all the check marks. In this case, they are Rust and Cyclone. So at this point, I'm sort of obligated to tell you a little bit more about Cyclone. So Cyclone is this research programming language created by very smart people that gives you memory safety without a garbage collector. That was sort of the main thing about the language Cyclone. And sort of one of the interesting things about Cyclone is that it was specifically designed to be a successor to C. It was not designed sort of as a brand new language. It wasn't like, we can do these crazy new things. It was like, hey, we kind of like C, but the whole memory unsafety thing, we don't want that. So what do? They created Cyclone. And in fact, Rust was heavily inspired by Cyclone and other languages in that domain. Okay, so we have Rust and we have Cyclone. There can only be one winner, so what do? Well, you know what I chose. But I sort of took a look at these languages. I wrote a few other operating systems in these languages. I wrote more code. I wrote some file system code. I wrote some virtual memory code. I just started writing more code to see if one of these languages sort of emerged as the winner. At this point, I should tell you a bit about the history of Rust. At this point, Rust was in version 0.5 or 0.6. This was 2013. And it was a very different language than it is now. If any of you guys write Rust, it is not the same language. That being said, I was really impressed with the language because not only did it have these 4 properties that I was looking for, it had these additional properties. It allowed me to write high-level abstractions like functional-looking code. That was pretty cool. It allowed me to do like memory allocators in this way that I could convince myself that they were correct. It also had a build system. That was a revelation that I could actually write an operating system and do like cargo build, and then it would build my operating system. That was insane. I mean, for those of you guys that have written C, you've written a makefile, you've used libtool. It's terrible. We don't want that. And it was incredible that I could write a little TOML file and cargo build, and my kernel would be built. That was insane. And not only did it have these 2 things, and this third one really tripped me up. I was very confused about how this was possible, but it was data erase free. On its web page, it said, Rust, if you write your program in Rust, you cannot have data races. And I didn't know what magician was creating this language, but I was really, really blown away. And so clearly, Rust sort of won this battle here, and this talk is about making a case for Rust. Yeah, clearly I like Rust. Rust is a good fun language. So that's how my sort of love affair with Rust started. With operating systems and system software in general. So the way I want to structure this talk is by first telling you why we should care. Sort of this was my research, and I cared sort of because I had to graduate and because I just generally cared. But why should you care? Well, when we write software, we have bugs. We write bugs because we are human, and it is hard to write good software. It is hard to write secure software. If you build a house, you probably want to use more than just a hammer and nails. You probably want to use all the tools at your disposal to make this house as nice as possible. And not only that, but if the people building the house could tell you, hey, the roof, it's never going to cave in for the next 65 years, guaranteed it's not going to happen. Like that, you'd probably hire those people instead of the people who use hammer and nails. So, I think we should build software the same way. Let's use the right tools. Let's get those guarantees. Let's, build this house nicely. And, there's a lot of research that tells us that C and C++ are very ill-defined, much more so than we sort of thought. And you can read countless of research papers that tell you this, but you don't have to read research papers to know that C and C++ are sort of not what we should be doing. You can just read the tabloids, and you can see that Equifax lost $600 million because they had a bug in their program, or because Yahoo lost $35 million because they had a bug in their program. And because all of these people's data was just gone, and cryptocurrency is just gone, and money is just gone, and people's infidelity is exposed, and things of this nature. So clearly, there is a problem. And everything that I do, this is actually something I discovered recently, everything that I do is about creating tools to help us prevent these kinds of issues in some guaranteed fashion. It's cool if the tool helps us. It's cooler if the tool prevents us in a guaranteed fashion from doing the wrong thing. And I genuinely believe that Rust is in this class of tools. It is a tool that prevents us in a guaranteed way from doing all of these wrong things. And I think it is exactly the kind of tool that we should be using when it makes sense. Now, it's not the only kind of tool. There are other really great tools. But this is, I think, probably the best tool we have at the moment, especially for writing system software. OK, so this is how I'm going to structure the rest of the talk. That's sort of the introduction here. So first, I'm going to tell you about Rust's guarantees. And this is where I'm going to spend the majority of the talk. In particular, I'm going to tell you about how Rust guarantees memory safety and race freedom. It turns out, I would imagine that most people who write Rust probably don't actually know how it happens. And that's because it's sort of weird, and it doesn't totally make sense unless you think about it for a long time. But I'm going to tell you how it works. And then I'm going to tell you how to use Rust to get more than just memory safety and data race freedom, and these things that are just part of the language. And I'm going to do that through examples. I'm going to show you a web framework that I've been working on called Rocket, and then I'm going to tell you about an operating system that I've been working on called Osmium. And Rocket is kind of cool because it has compile time security and safety guarantees for the web. Things like if your web application compiles, you will not have a CSRF attack. You will not have a cross-site scripting attack. You will not have a directory traversal attack. The thing compiles, these things are guaranteed. And Osmium, where you can write device drivers, and they will automatically be verified for you. I'm talking about formal verification. You write your device driver in a certain way, press the button, and it goes and verifies it for you. And then finally, because Rust is a scary language to learn, I'm going to tell you about how I taught Rust at Stanford in a brand new operating systems class where undergrads, masters, and PhD students wrote an operating system in Rust. And hopefully I can convince you that it's not too crazy of a language to learn. OK, so that's what we're talking about. Let's start with Rust's guarantees. So Rust is a programming language being developed. Well, the funding for development is primarily by Mozilla Research, but it's an open source project. And as we sort of already learned, it is memory safe without a garbage collector. You cannot have data races if your program compiles. The runtime is fairly non-existent. It is smaller than C++'s, for instance. You can do functional programming. You can have high-level abstractions. You can have structures and methods and all this kind of nice stuff. It has a really good build system called Cargo, and it has powerful macro systems that let you meta-program in kind of the way that you want to. And we're going to look at each of these things in sort of detail. We're not going to talk too much about Cargo, but everything else we're going to talk quite a bit about. So let's start with memory safety. So if we're going to talk about memory safety, we sort of have to define what memory safety is. I think we all probably have a, some kind of intrinsic belief about what memory safety is, but I'm going to go ahead and define it precisely for you. So memory safety, I'm going to define memory safety as follows. If you have a reference, then a dereference of that reference, we're going to say it's always OK. And if your language has a property that a dereference is always OK, then we're going to say that this is a memory safe language. And by always OK, I mean that the dereference always succeeds, as in you don't segfault, you don't just crash. And it always points to a value of a correct type. If you think you have a struct that looks like this, and you dereference it, then a pointer to that thing you dereference, then you have a struct of that thing, and the language will guarantee that. So that's our definition of memory safety. Now, this definition is actually very strong. It has all these implications. In particular, so one, first of all, just as a direct application, is if you have a reference, then you dereference it, then you always get a foo. If you have a reference to foo, and you dereference that reference, you always get a foo. Pretty easy. Well, what does that mean? Well, that means that none of these things have happened. You don't have a null pointer. It points to a valid memory address. You don't have a dangling pointer, which implies you don't have iterator invalidation. You don't have use after free. You don't have double freeze. And there are no out-of-bounds accesses. You have a vector of size n. You never access anything outside those n elements. And this one's weird. This one's different. You don't have data races. This is weird because we have about every single language that claims to be memory safe does not prevent memory races. And I argue that none of those languages are actually memory safe, at least according to my definition. That includes things like Java and Go, and yes, Haskell. All of those languages are mostly memory safe, but they almost all have this little escape hatch where if you do things concurrently in a certain way, all of a sudden you'll get a dereference to a type and something else will be in its position. And so these are our constraints for memory safety. So yeah, so no data races. That one's pretty important. Okay, so memory safety in Rust. So how do we get memory safety in Rust? So this is the formula for memory safety, in particular in Rust. So the first thing is that Rust will force you to initialize everything. You can never use something until it's initialized. It will also restrict the way that you alias values. The pointers that you can create to memory, those can't alias under certain conditions. And finally, it has this concept of ownership that we'll talk about later. But the main idea behind ownership is that you cannot, or rather that the language always tracks who is responsible for a given memory address. Who's responsible for freeing it, who's responsible for allowing references to be created, that kind of thing. And if we sort of add these three things together, we get memory safety. And so I'm going to tell you how these things sort of work. Okay, and right, so one property here is that all this is actually happening at compile time. So if you guys are familiar with Java or Go or anything that has references and is garbage collected, you can still have null pointers. And if you dereference them, then you'll get a null pointer exception. And that's within the class of memory safety because if you think about it sort of formally, what's happening is you dereference a thing, and then it crashes your program. And so that's OK because nothing executed afterwards. And so we're just going to call that memory safe. But in Rust, this is at compile time. There is no such thing as a runtime check, except for out-of-bounds accesses because the type system isn't expressive enough to sort of do the right thing otherwise. But in Rust, all of this stuff is happening at compile time. So how does this sort of magic work? This is pretty magical. Well, let's talk about aliasing. Let's talk about what goes wrong when we have aliasing unrestricted in the fashion of C++. So here's some C++ code. If you're not familiar with C++, that's OK. Just follow along with the pictures on the right here. So this is some code that is creating a vector. It's pushing a string to that vector on line 2. It's getting a reference to that string. Then it's pushing a second string to that vector. And then it's printing out the string that was referenced the first time around. And if you look at this closely, you'll spot a bug. And this program will more than likely segfault. So what's going on here? So let's look at this line. So on the right here, I have sort of each square is a memory location, and each line is a reference to that memory location. So when we do a v.pushback, then the vector v gets a reference to its contents. In this case, it just has one, v0. In the next line, we create a reference to that v0. And so now we have x pointing to v0. In the next line, we push a new string to this vector. And what's going to happen is, well, we don't have enough memory to hold this other string. And so the vector is going to have to deallocate the current contents, and then allocate more memory, copy v0 into that memory, and then it has a spot for v1. But now this is a problem because x is holding a reference to x0. And so x is now a dangling pointer, and if we were to execute that next line there, then we would probably, ideally, we'd segfault. In fact, the compiler is written so that it's segfault so that you can catch it. OK, this is sort of not good. This is exactly the type of thing we're trying to prevent with Rust. So where's the problem here? What's going on? Well, the problem is in this line here. The fact that we had these two references, these aliasing references to the same memory location, and then something else came along and all of a sudden changed the reference from underneath us, that is a problem. So the problem is that aliasing is really, really hard. And so how do we fix this? How do we get rid of this aliasing that we don't want? Well, one very easy way to do this is to say no aliasing. You cannot alias anything. There's just a single reference to a thing, and that's it. You have nothing else. This is actually a very popular idea. It sounds a little weird, but it's a popular idea known as a linear reference or a linear type. And the idea is that you could choose either A or B. You could choose for v to reference v0, or you can choose for x to reference v0, but you can't choose both. Choose one. And so clearly, we can't deallocate v0 while something is holding a reference to it, because in order to deallocate it, we're going to need a reference to it. So this would solve the problem, but this is way too restrictive. I mean, we're certainly used to aliasing is OK, except when it's not. So we want something in the middle. So we don't just want to get rid of references, of aliasing rather. We want to restrict aliasing. We want to have some mechanism by which the good aliases are allowed and the bad aliases are denied by the compiler. So what do we do? Well, the sort of insight here, this is the sort of main insight from Rust and from literature that Rust borrows on, is that it's OK to have aliases as long as if you have multiple aliases, none of them can mutate the thing being aliased. And so that means that you have, in this case, you have three choices. Choice A is that you can have n immutable aliases, you can't change the thing being aliased. Second choice is you have exactly one mutable alias. And so in this case, we have two possibilities. Either v is mutably aliasing v0, or that should be x. X is aliasing, mutably aliasing v0. But that's it. There's no other choices. You have n immutable aliases or one mutable alias, nothing else. This is exactly what Rust will do. Rust will do exactly this kind of restricted aliasing plus ownership, which turns out is important, and you'll see in just a second why. OK, so let's take a look at how this actually materializes in Rust. So here is ownership and restricted aliasing in Rust. So first part is we do have some sort of linear types in Rust, actually. And in particular, we have this concept of ownership. And the idea is that something actually owns the value. It's responsible for it. And it can let go of ownership, but then it can never touch that value again. If you have a book and you give it away, the book's gone until someone gives it back to you. But you can also lend someone the book, and then they can give the book back to you when they're done, but you're still the owner. And Rust, in fact, encodes the exact semantics of ownership. So this is what it looks like. This is some Rust code. So you have let x equals some person, and then you assign x to y. Well, then you've given ownership away of that person to y. And so you can never touch x again, and this would be a compile time error. Similarly, if you pass it to a function, well, now the function owns the value, and passing it again to a function would be a compile time error. You can also do this with methods. So you have a method m that takes self as a receiver, then you cannot call it twice because it gets moved into the method. But we still want aliasing, and if we want to get aliasing, then we have to borrow instead of give away. And so this looks like this. So this is something that's not allowed. If you have a person and then someone borrows the person from you, that's a strange concept, but if someone borrows the person from you, in this case we use the ampersand to create a pointer. A borrow is just the pointer. Then we can't give it away because someone else is borrowing at the time. So you lend the book to your friend, you can't possibly give it away to your other friend. The book is not in your hands. But you can borrow it again. So this one does not fit the book analogy. Clearly you don't have more than one book to give out to your friends. But I'm sure you can shoehorn the analogy if you'd like. I don't know, you lend it to a friend, the other friend goes and reads it from that friend, something like that. But they can't scribble on it or something. So you can't have a mutable reference to a thing and an immutable reference to the thing. So two immutable references, OK. A mutable reference and an immutable reference, not OK. Also, you can't have two mutable references. The rule here is one mutable reference and no references, no other references, or n immutable references. And the same thing happens with methods. So if you have a method that takes a mute self, then it will mutably borrow it. But the caveat here is that once the method returns, as long as that borrow isn't stored somewhere, then you can borrow it again. It's like they gave it back to you. So you can call this method twice, because after the first call, the borrow is returned. OK, so that's what's going on with Rust. This is how it pans down in this example. Here's the C++ code. Here's the Rust code again. Let's look at why this code won't compile in Rust. So here's the code. We'll start at the beginning. We push this string. V now holds a reference to it. Now x holds a reference to it. And we try to push this other string. And what Rust will say is, whoa, in order to push that string, you have to be able to mutate the vector. But hey, there's currently a reference to that thing inside the vector. So clearly, you shouldn't be able to mutate the vector. And then it says, sorry, this breaks the invariant of having either one exclusive mutable reference or only immutable references, so this code is not going to compile. Now, I sort of blindsided you a bit there, because sort of this method, this push method, calls push on v, not on v0. Right? So these are actually distinct memory locations. V and v0 are distinct memory locations. And push will create a mutable reference to v, not v0. So what's going on here? Well, this is where ownership sort of plays a role here. So what happens is push comes along, and it takes a mutable reference to v. And then through Rust ownership semantics, Rust knows, oh, v actually owns v0. So if you're going to be able to mutate v, then you're going to be able to mutate v0. And it will implicitly create this solid line to v0. And that's where the aliasing constraint is actually broken. OK, so this is exactly how Rust does its magic. There is a research paper called Rusty Types for Solid Safety, where I've actually formalized these semantics, and I've proven that this is in fact memory safe. So if you care to read programming language literature, then look up this paper and enjoy the math. OK, so we sort of skirted the idea of race freedom, but this should be somewhat obvious at this point. Well, race freedom is defined, you are race-free if at most one writer exists to a memory location at once, right? Because a data race is there's at least one writer and some other reference to it, both accessing the memory location. So clearly, if the language restricts you from having more than one writer when anything else exists, then you will be race-free. And that's true. OK, so if we have these semantics, then are we data race-free? Well, the answer is yes. But so is that it? Cool. Is that how Rust does data race freedom? Well, yes, but it turns out that this kind of sucks in general. So let's say we have this program here, and we create a mutable reference to 0. And then in 2 different threads, we try to lock that reference and then increment it, and then lock the same reference and then increment it again. This is totally race-free. Each thread has exclusive access to this variable, right? And so, ideally, the language would be like, yeah, sure, I can see that you're locking it. I can see that there's no way you can actually access this mutable reference at the same time in 2 different threads. But what the language actually sees is that when you do this, ++ on A, you need a mutable reference, because you're going to mutate this thing. And clearly, you're going to have these 2 mutable references in 2 threads, and Rust is going to say, nope, sorry, that does not hold. So this breaks the invariant. You are not allowed to write this code. And in fact, if you try to write that code right now, it would not compile. And so, strangely enough, concurrency is impossible with safe Rust because of this restriction. If we have concurrency, then we're going to be writing from 2 different places at once. Ideally in a race-free way, but Rust cannot know this statically. These are dynamic guarantees. And so concurrency in Rust is not actually possible with the language. And so concurrency actually has to be provided by libraries that use this construct called unsafe to implement concurrency. It's an escape hatch to the language's semantics that effectively allow you to say, hey, Rust, I know what I'm doing. Now, this is a bit of a misnomer because unsafe code can't be wrong. Unsafe code has to maintain every single guarantee that the language itself will maintain. Some people don't like the word unsafe. People argue that we should have used the word safe instead of unsafe, but there you have it. So the idea here is that libraries can tell Rust, hey, I know what I'm doing, and maintain the invariance that it does statically, dynamically. And this, in particular for concurrency, you're going to do a particular kind of unsafety called interior mutability. And the idea behind interior mutability is you're going to dynamically ensure aliasing restrictions using this escape hatch. And what it's going to look like is you're going to have this function that takes a shared reference, an immutable reference. So you can have a bunch of them, and it's going to give you a mutable reference. Now, you cannot write this function in safe code, but we can write it with unsafe code. Here's sort of the simplest way to write this interior mutability thing. Here is a function, and you don't have to worry about most of it. But the part that's important here is this atomic compare exchange thing. So what we're going to do is dynamically check that exactly one thing, using the hardware's idea of atomic operations, exactly one thing is going to be able to get a mutable reference when this function is called. Right, so in this case, this is actually much worse than we had it before. So if you look at this function, this says, hey, given a value, you're going to be able to get one mutable reference for the lifetime of the program. And if you ever try to do anything else, we're going to crash. This is actually way worse than Rust's static guarantees. But it illustrates the idea that we can have these functions that give you shared references and then give you a mutable reference as a result. And they can maintain Rust's aliasing guarantees at runtime instead of at compile time. So here's a better example of mutex. This is how mutex is implemented in the standard library. So in the lock function, we take a shared reference to a mutex, and then we effectively do this atomic compare and exchange. And while the thing is locked, while we cannot atomically guarantee that we are the sole owner of this thing, then we're going to spin. And as soon as it's ready, we're going to create this unsafe cast to a mutable reference. Now, we sort of want to know when this thing is ready to be, another mutable reference is ready to be created. And so in the destructor for the mutex, we're going to do exactly that. We're going to set it from being locked to being unlocked. And now, let's go back. And so now, what's going to happen is we create this locked thing, and then you can use it as however you want. As soon as it gets destructed, and we know that it's a unique destruction because of Rust's ownership rules, then we're going to free the lock, and everything is nice and dandy. And so this is how you regain concurrency in Rust, even though the language itself prohibits it. And so now we can actually write code that looks like this. We create a mutex to some variable. We lock it plus plus. We lock it plus plus, and we're good to go. And you actually see that this is actually nicer than the code we wrote before. It's nicer than the code we write in C. So it's pretty cool. But yes, you cannot do concurrency in safe Rust. Pretty weird thing. OK. So that's all I want to say about Rust guarantees. Now, the next parts of the talk are much smaller than the first part here. So the next thing I want to talk about is doing more than just memory safety. And I'm going to talk to you about Rocket, this web framework, and about Osmium, this operating system. So here's Rocket. This is Rocket's logo. I like it, so I put it up. So Rocket is a web framework for Rust that makes it simple to write secure, correct web applications without sacrificing flexibility or type safety. Secure, correct, flexible, and performant. This quadfecta of things. That's what we're looking for here. And so just to be clear, when I say web framework, I mean like a Django or like a Spring or like a Rails, that kind of thing. So Rocket is somewhat, it's been around for a little bit. 2016 was when it was released. Released 0.2 after that, 0.3 after that, and there's an emoji font missing on the machine running this. But that's a little star. That's a GitHub star. It's got like 4,500 GitHub stars. So people like it. We've got tens of thousands of users. We have some people using it in production. NPM is actually running services in Rocket in production. System76, laptop makers are running stuff in production. Mozilla, I don't know what they're doing, but they have a bunch of things written in Rocket. I don't know if they're deploying them or not. But people are using this thing, so that's cool. And so when I say secure, particular, I want to be very clear about what I mean. And that's that we have all of these problems with the web, and we don't want these problems. And Rocket fixes the problems, ideally. And I separate these into 3 categories. This green list are the things that are, if you don't know web stuff, that's OK. This green thing, I say we have pretty good ideas about how to solve them. This yellow thing, this yellow stuff, we have solutions, but they're not guaranteed solutions. Nothing stops you from circumventing them easily, or just accidentally. And then these couple of other things have no good solutions to them. You write a Rails app, you can misconfigure it all day, and nothing's going to tell you that you've done the wrong thing. And so what Rocket's going to do is, for these green things here, it's just going to use the existing solutions, except it's going to guarantee them. If your thing compiles, you cannot have these issues. These middle things, we're going to have new solutions, and again, they're going to be guaranteed. And the red stuff here, we're going to have brand new solutions, and again, we can't guarantee them, but we're going to try really, really hard to steer you in the right direction so you don't get it wrong. And ideally, if we do a good job, everything turns green, and we can go home and write web apps all day and not worry about what's going on. OK, so this is what Rocket looks like. I'm not going to spend too much time telling you what's going on, but a few things that I want to emphasize. First, I think this looks, it's pretty cool if this looks this way, and this is like a C successor. This looks, I think it looks kind of like Python. There's also question marks and, exclamation marks in there and stuff, but ignore the exclamation marks, or the question, whatever. Ignore all the weirdness and focus on the coolness. That's how I sell things. Ignore the weirdness. Focus on the stuff you like. I also feel like that's how relationships work. Just focus on the things you like, and you'll be happier. All right, enough of life advice. OK, so here's what's going on here. The first part is this top thing, where you effectively specify how requests are going to match this thing. So in this case, we're going to match get requests to things that have an ID parameter. And then the second thing here, we're going to validate each of those things using a type. We're going to specify a type for each of these things. And so we're going to say ID is going to be a paste ID. Now, there's this other thing here, user, that is not present in the attribute. And what this is called, it's a request guard. It's a way for you to give Rocket an arbitrary type and say, hey, this is how I validate a request that is supposed to contain something that, in this case, is a user. And so you might imagine that the functionality for validating a request to have a user is you look at the cookies, you go check the database, you check expirations and whatnot, nonces, and then you say, yep, here's a user. And then finally, you write the code to do the work, and you output some type. In this case, this is like a paste bin example. So you're retrieving a paste bin for some user, and you're going to return maybe a file if the file was there, and maybe not if the file wasn't there. But the neat thing is here, you write only the code that is going to sort of act on the good stuff. Everything is validated before the code runs. And here's one interesting case of sort of using this functionality. Here is a static file server written in Rocket. It is exactly 4 lines and is guaranteed to not be vulnerable to directory traversal attacks. A directory traversal attack is when someone gives you a path and because of the string that they gave you, all of a sudden you give them whatever file they want. And clearly that's not good because we have sensitive files on our machine. And the implication here is that, as I just said, handlers are only called in validated data. And there's some magic going on here with type classes and traits and whatnot, but the gist of it is that this pathBuff type does this validation, and if you get a type of pathBuff in your handler, then you are guaranteed to be able to use this type to open files and do whatever you want. Okay, so that's Rocket. There's the website, rocket.rs. I know, you're looking at me, I see you, yeah. I'll be done very soon, I assure you. This is the website, you can go there and check it out. All right, I'm gonna breeze through the rest of this. This is Osmium, it's an operating system. Here is what it does. You write device drivers in Osmium. You encode a state machine in Rust, and it looks like this. And then the second thing you do is you write these little implementations that effectively allow you to query the device for what state it thinks it's in. And then you connect the machine to something we call a monitor, just another machine. And that's literally it. You do these things, you write your driver in a certain way, you write these little methods that effectively look at unit tests, you connect the machine to another one, and then you press play. And it will verify the device driver for you. And the gist of it is that because Rust is so structured, because of ownership types, then you can directly encode the state machine in Rust. We can read the state machine off from the types. We can run the state machine. We can generate code that runs the state machine and checks it against the device's state machine and see if they're equivalent. And if everything says yes, then everything works out. All right, that's Osmium. Last thing, 2 minutes. Teaching Rust. I think it's actually pretty important that I get to this part because for those of you that haven't learned Rust, my guess is one of the big reasons is because you're like, this is a scary language. And it is kind of a scary language. And so I taught this class at Stanford called CS140E, a brand new class that I designed and taught at Stanford for the first time. And this was the deal with the class. The students were going to learn OS fundamentals. They were going to write an operating system. They were going to build an OS from scratch in Rust for the Raspberry Pi 3. They're going to learn embedded development fundamentals, and they're going to write drivers and all neat stuff. A bit about the cohort for the class. I asked them, have you implemented any bare metal software such as bootloaders or device drivers? And what is that? 71% said no. And then I asked them, hey, what do you write software in? And they said C, C++, Java, Python, JavaScript, and 1 or 2 people said other things. But 0 people said they had written Rust. So there were about 25 students in the class, and none of them had written Rust. Here are the key takeaways. So first, the students were comfortable with Rust in about 4 weeks. And about comfortable, about 4 weeks. Give or take comfortable, give or take a week or 2. Every single student wrote an OS successfully in 10 weeks. And the OS did interesting things. It had a memory allocator, it had a file system, it had device drivers, it had exception handling, it had processes and context switching. This is a real OS for 64-bit ARM and a multi-core platform. And not a single student used GDB. This is insane because in the original version of this class, CS140, GDB was taught. You spend a week teaching GDB to students because they will segfault and crash so much. Not a single student used GDB. So I think if you want to check it out, cs140e.stanford.edu, I think this is a good example of that Rust is teachable and learnable. Okay, so that's all I have to say. I'm way over time. Thank you for letting me be over time. This is what we talked about. This is me. This is my email address. If you guys have any questions on any of this stuff, I'm more than happy to talk about it. I have a workshop as well on Rocket. If you want to learn more about how Rocket does what it does, please come to the workshop. Thank you so much for your time.
Well, thank you, Sergio. We have one question from the audience,
Yep.
and that's how big of a catastrophe do we actually need in order to start writing code in a safe language?
Yeah, I think we've had enough catastrophes that I think people are aware. So I've been talking a lot to people in industries where correctness and security really matters, in particular people in the autonomous vehicle space. And they are really, really, really tired of C and C++. People at SpaceX are really, really tired of C and C++. I think people are happy with the number of catastrophes that have occurred, and they are ready to move on to the next thing, but they don't feel that the thing is ready. They don't feel that Rust is ready. They don't feel they can hire the people. So I think it's less of a, when are people going to get their minds together and do the right thing, and more of how can we as a community that creates Rust, make it such that it's an easy step to take.
Well, thank you.
Yeah,
and
absolutely.
we now take some questions from the audience.
Cool.
If there are any, please raise your hand.
Have you had catastrophic incidents written in Rust yet?
Catastrophic? No. Thankfully, I don't write software that can like ruin people's lives. I don't know. I guess Rocket might ruin people's lives. I don't know. So I think there are. So I can use the class as one of the examples to answer your question. I think. So one of the things that they wrote in the class was this memory allocator, and obviously, writing a memory allocator, there's no way that the language can prove that it's memory safe because it is the thing dishing out the memory. So it's not going to be able to prove this thing to be correct. And so there was unsafe code in this memory allocator. And so students had bugs. And their OS would run for like 10 minutes, and then it would crash. And still, they didn't use GGB, just a bunch of print statements. But this was not fun. And the takeaway from that is not that we shouldn't use Rust because, hey, it's not going to work anyways, but that we should use Rust better. So it became very, very clear what we could have done as the people designing the operating system that they're writing to prevent all these things from happening. We could have written the interfaces in different ways that would have prevented 99% of the bugs that they had in that memory allocator. And so I think because Rust is so new, it's not obvious how to do these things to prevent ourselves from messing up. And I think we're going to keep learning that stuff. And catastrophes will happen along the way, but I think at a much lesser degree than we're used to. Yeah. Sure.
Are there any more questions?
Hello. So in practice, when I'm at work and I want to deploy software and go home, and I have two mutable references and the compiler goes off, and I can just wrap it in unsafe and deploy and go home. Is that how it works?
That is how it can work.
Great, thanks.
It is ideally not how it works. It turns out it's actually pretty rare. I've written a lot of Rust code, probably hundreds of thousands of lines, if not more. And the number of times that I have to use unsafe are in the lower, double digits, maybe 15 times or something like that. If you look at the Rocket code base, it's doing some complicated stuff, and there's maybe like 5 uses of unsafe, about 2 or 3 of which will just go away as soon as the compiler gets better. And so it turns out that like these restrictions are actually pretty okay for the most part. Yes, people have to be very clever and write good libraries so that you don't have to use unsafe yourself. But the nice thing is that we can encapsulate unsafety in a library and expose safe interfaces that hopefully the unsafe code maintains its correctness. So I think it is scary to say, oh my gosh, I need to write this data structure. I need 2 mutable references. I want to go home. I am done with this web app. Like I should not be worried about this as a web app. But in practice, it comes up pretty rarely, especially for writing web apps. Rocket actually takes care of a lot of this for you. So I wouldn't be too scared of the restrictions because they're pretty easy to deal with and they don't come up that much in practice.
Perfect. Hey, thank you very much, Sergio.
Absolutely.
And we will have the next talk at 11, so in 10 minutes, with Bodil Stoke about immutable data structures and why you want to use them. Thank you very much.
Thank you.